Today, we're going to take our discussion of function rules and we're going to start doing some graphing. So, we're going to be using that coordinate graph paper I handed out. You are welcome to take out a piece of that right now. If you're in the classroom, there are copies of it on the table, in the back of Mrs. Marino's room, in the back of my room, but also I gave some out to everybody. For the folks at home, it is in the reference section on Classroom. If you go to the classwork tab all the way down to the bottom, there is paper there for you to print. You can use regular graph paper as well and just draw the coordinate axes on there if you need to. So today we're going to model functions using rules, tables, and graphs. Those are 3 of the 4 ways we can really show a function. The other one is, of course, words and application problems. More on that to come. So again, you're seeing 3 ways here. That's what we're going to be working with today. We're going to start with a function rule. This would be our algebraic representation. A function rule is an equation that shows how the variables, the input and the output, are related. Remember our last discussion, we were talking about independent and dependent variables. We're going to make a table of values. That table identifies specific input and output. We're going to choose those. We can't pick all the points because there's an infinite number, but we're going to make some choices, and I'll give you some hints on some good ones to pick. And that would be a numerical representation. Finally, we're going to take that table and we're going to graph that function, and that gives a visual picture of the function, and that would be a graphical representation. So how we're going to start is here's sort of 3 representations of the same rule. We've got a rule here that we take the input variable, multiply it by 30, and that gives us the output. We have a table of values. So if you notice, if I take that g of 0 and I substitute it into this function rule, 30 times 0 would be 0, and 30 times 1 would be 30, and 30 times 2 would be 60. And you can see that this is the table that represents, or I should say a table, that represents this function rule. And then we're going to come over and we're going to do a graph. So now I want you to remember your coordinate points. This is your x coordinate. This is your y coordinate. So 0, 0 would be the origin. We have 1, 30. So 1 in the x direction. X is always horizontal. It goes left or right. And then your y always goes up or down. So 1, 30 would be here, and 2, 60 would be here. And then I'm going to connect those points with a line. You're going to see actually this is a ray because this is a real world graph and I can't have negative gallons or negative miles. So it has an endpoint here. There's no arrow down here, but you'll see the arrow up here. So this is a real world application that shows a function rule, its coordinating table, and of course its graph as well. So let's start right now. We're going to say, what do we do? How do we go from a rule to a table? So let's start with a function table that organizes the input, the rule, and the output of a function. So the function that I'm going to make a table for is this one right here, f of x equals x plus 2. So what I'm going to do is I need to pick some input values, some values for the independent variable. This is what I get to choose. Right now, you could choose, and I like to do 5 different inputs so I can see what the function's doing. But you could pick negative 20, you could pick 40.5, you could pick 1,142,000. You could pick any values for this input. Now, I'm going to introduce you to my 5 favorite. I call them the Fave 5, and here they come. Drum roll, please. Da, 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 da. There they are. Negative 2, negative 1, 0, 1, and 2 are my favorite 5 inputs when they are allowed as part of the domain. For instance, a second ago we were talking about gallons. Negative 1 and negative 2 wouldn't make sense in that context. They wouldn't be part of the domain of that function, so I would not use those. However, I do like to use 2 negatives if I can because, well, you'll see in a minute, sometimes interesting things can happen on the negative side of things. So again, we're going to use 5 inputs. We try to choose 2 negatives unless they don't make sense. And the reason I like these 5 is they're close to the origin. So points are most likely to fit on my graph. So here comes the fave 5. Again, I chose them. And now I'm going to substitute each member of my domain that I've chosen right now. I don't have the full domain. These are just 5 members that I've picked. And I'm going to substitute -2, get the output, substitute -1, get the output, and so forth. So -2 plus 2 is 0. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. And 2 plus 2 is 4. And if your inputs are in a pattern, guess what? Most often your outputs will be as well. What I have just created is a table of values that in a minute we can talk about graphing. But that's how we make a table of values. So it's your turn. This time the function is f of x equals x squared. I'd like you to make a table of values. And I'm going to let you know that hiding behind the x for mine is going to be the fave 5. That's not the only numbers you can choose. However, to do the graph, that is sort of oftentimes the best choice. So pause the video, put your 5 x's in, and then put your outputs accordingly. Okay, let's see how you did. So now, guys, if you pick 5 different inputs than mine, your table is going to look different than mine. And it doesn't mean it's wrong, but you're not going to be able to kind of compare to what I've done here. So got to be careful. What is -2 to the second power? I'm praying, I'm hoping that you said +4. Remember that we catch it in the gloves. And -2 times -2 should be a +4. Same thing with the -1. And then 0 squared would be 0. 1 to the second power would be 1. And 2 to the second power would be 4. And you'll notice kind of an interesting symmetry happening here. Okay, and that's what we're going to talk about. And that's why it's important to get those negative inputs. So that's how we make a table of values. So now let's take it from that table of values to a graph. You know, how do we go from a rule to a table of values to a graph? That's our next step. So we're going to take this one and we're going to go all the way from the start to the graph, okay? So again, f of x equals x. Whatever input I put in, the output is the same, okay? So guess what's behind the x? Oh my goodness, what could be back there? The fave 5, there they are, okay? So if I input -2 for x, f of x is -2, and this gets pretty boring pretty fast, right? Because whatever goes in comes out the same. Now, the next thing that we're going to do is once we have this, we're going to look at these as coordinate points. So I'm going to come up here and I'm going to grab a point and I'm going to plot -2, -2. So start at the origin. The first number is left, right, or since it's negative, we're going to go 2 to the left. The second number is up, down. Since it's negative, we're going to go down. And we're going to put that guy right there. And then I'm going to grab another point and I'm going to graph -1, 1. Except I didn't grab him. Let's try that again, Mrs. Woodruff. There he is. And then I'm going to grab the next one, which would be 0, 0. And what I should see is some sort of kind of pattern happening here. And I should see some kind of function that I can start to say, oh, that's interesting. Look at that. And then the final one is 2, 2. And what do I have? I have a line. Guys, this is going to be a linear function. Now, I'm not done. Because yes, these are my 5 points, but somebody in class could have picked -5, and -5 would be also a solution to this. Somebody else could have picked 7, and 7 would be. So in order to get, and of course somebody loves fractions, and they would have picked 1.5, 1.5, and that point should be here. So we don't just leave those 5 points. We're going to connect them with a line, and there should be an arrow on both ends because I know one of you really wanted to graph the point 1,000, 1,000. So by putting our line in and our arrows, we're saying that all these points make this function possible. And there is the graph of f of x equals x. And yes, it is a linear line, linear function. So, do you connect the points? Do you extend it in both direction? It really depends on a real world situation. But when we're just talking about algebraic graphs right now, if we got these points as part of it, we would sort of make this graph. We are going to talk about this special guy in a second. So, when we're dealing with real world situations, we'll have to think about what points make sense. Do fractions make sense? Do negatives make sense? That type of thing. But as we're just plotting algebraic graphs here, you're going to see that we're going to extend them. We're going to connect. We're going to put arrows to show that continuity. All right, so now, how do you go from a rule to a graph? Well, the answer is, whoops, I forgot to uncover this. The answer is that we're going to go through a table. So you get a function rule, you make a table, and then you're going to do the graph, much like we just did. So let's say that you've got to graph this, absolute value function. Okay, this is something we actually talked about just a little while ago. So I want to graph this guy. So the first thing I'm going to do is make a table. When I go to make that table, I'm going to put my faves on there. And you might notice that I actually went beyond the fave 5. You're going to pretty soon learn what this guy should look like. And if you're sort of not seeing the picture you're expecting, sometimes you're going to have to go beyond the 5 inputs. The 5 are going to be okay here, but sometimes you need to do more than just the 5. Okay, there's the fave 5. So I put in -2, and the absolute value of -2 is +2. Absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. Hey, notice that duplicate answer there. Okay. Absolute value of 2 is 2. And if we kept going, it would look like this. And then again, we're going to come and we're going to graph those points if they will cooperate with me. There we go. So -2, 2. And then we're going to plot the -1, 1. And we're going to really get that point this time. And we're going to plot, and I won't plot them all because you're going to see what's happening here. But right here, notice that it does a turnaround. And now it goes positive. Do you remember that absolute value functions are always positive? So notice that our y's aren't negative, and our graph is not going to go below that x-axis because then that would mean the output is negative. So basically what you're seeing here is a V. And guess what? Absolute value functions will form a V. Matter of fact, we were just looking at one a second ago. I can tell you right now, this is an absolute value function, even though I don't see the rule. Pretty cool. Okay, so the next thing I am going to do is I'm going to connect to these and put the arrows on. So there would be the graph of f of x equals the absolute value of x. And we talked about this recently, saying, remember, you can get 3 kind of solutions to an absolute value equation. You could get 2 answers, like look at the 2 and the 2. You can get 1 answer, look at that 1, 0, or all of these values down here are never used. Here's your no solution. So an absolute value function can have 2 answers, 1 answer, or none. Pretty cool. Okay, let's do a little bit more practice on this one. So what I'd like you to do is have a piece of graph paper. I want you to make a table, and I want you to do the graph for this one yourself. By the way, I'm going to just tell you that you're not going to be looking for a ruler. There won't be lines to draw in this one. So go ahead, pause the video, create a table, plot your points, and come back when you've got it, and let's see how you did. Guess what's behind the x? There they are. And now you're going to see with the absolute value function in this one, why we want to have those negative inputs. So because things sort of change sometimes in that negative land. So I'm going to square the -2, square the -1, the 0, the 1, and the 2. And I'm going to plot those points. And what I'm going to see this time is I'm not going to get that straight line this time when I plot these. There's more of a curve. So this function that is squaring is giving me not a V, but more of a, can we call it a U? It looks more like the letter U. And I'm going to draw this in a second, okay? So I just want you to see that. We're going to draw that in a second. Now, before I do that, we're going to start talking about what is the domain and range of these functions. So I'm going to draw it in. I'm going to go to the next slide, which is going to show the answer. And then I'm going to talk about what this means down here. So my question for you, is there any number that we could not put in for the x? Is it okay to put in -10 as an input? Could we have put in -100? Can we put in, 1 million? So if you'll notice, all the inputs can go in. There's nobody that's not allowed. So for instance, we wouldn't want to put a negative under a square root. We wouldn't want to divide by a 0. But in the case of x squared, every number can go in. So the domain, the set of all inputs, is everybody, from -infinity all the way to infinity. And the way you can see this on the graph is just think about kind of all the possible inputs. And if this guy keeps extending, he's not really a true U. He opens wider and wider and wider. Eventually, every x would be covered by the graph. But let's change our thinking. Almost turn your head and think about what y's can come out. Can any of these y's down here, can -4 be an output? Can -3? No, the graph doesn't touch any of these. What is the first output? And you've got to turn your head and look at this sideways. Look at it coming from here, and the first output, do you see, is 0. That's the smallest output. What's the biggest output? Well, these arrows tell me it's going to go forever. So the range, the numbers that can come out of this function, are 0 inclusively, that's why the bracket's there, and everybody up to positive infinity. So the domain of this function, you kind of look along the x-axis, is everybody, and the range, you kind of look along the y-axis, is 0 inclusively up to infinity. Okay, so how about if we try this one? And again, I want you to try it yourself. I know on Edpuzzle, it's kind of hard to have a question, so I want you to pause it, and I want you to create a table. I want you to graph it, and this time I also want you to give the domain and range. And when you come back, before I show you the answers, I'm going to talk about these two questions. Okay, so hopefully this part is getting easier, right? There's the Fave 5. 6 minus 2 times -2. -2 times -2 would actually be a +4. And again, if you're having trouble with that, change this minus to plus a negative, and you probably won't. And if you did the rest, these should be your outputs. So when you graph these, you should be seeing a straight line form. So, we're going to start at -2 all the way up to 10. We're going to take -1 to 8. And if I keep going, they're all going to go. I'm just going to put the 2, and I could pick up my ruler, draw a nice straight line with arrows, and you can see a linear function, a line coming here. Okay, so now what I want you to do is to think about your domain and range. So when we're thinking about our domain and range, our question is, what x's can go in? Is there any restriction on an x going in? Is there any x we can't put in? And then the second question is there any y, is there any output that wouldn't come out? Okay, so I would draw my line through here. Can all x's go in? And your answer should be yes. And can all y's come out? And if you extend this line, you're going to see that they can. So for this linear function, it is everybody on both. In a second, I'll explain that again once I draw the line in. It's just hard to do it right now. So the other question I'm going to ask you is, what's f of 4? And what x gives you an output of -6? So here's two more questions with function notation. So when you see this is asking for what is the y if 4 goes in. So if you come up and put 4 in for x, you'd get 6 minus 2 times 4, or 6 minus 8. And your output would be -2. And this is why function notation is really cool, because if I just look at this, I can see the point. I can see that 4, -2 is a point that's going to be on this line. So that's why function notation is better than just having a y here. All right, now here's the opposite question. If y, or if f of x rather, is -6, then what would the x be to give you that? And sometimes we can look at the graph, and otherwise we would do the algebra. We would take -6 and substitute it in for f of x and solve for x, the two-step equation. Or sometimes you can simply look at the graph. So here I'm going to actually show you kind of on the graph. Let me just get back to where we were here. So if it's on the graph, you go to the y of -6 and say, what x gave me that? And your answer would be 6. So the point here is 6 comma -6. And that's kind of how we start just talking about graphing function rules. So I want to remind you that to graph a function rule, you need a table. The Fave5 will be your BFFs, guys, for the most part. Sometimes they fail you and you have to use different inputs, but for the most part, they're a great place to start. Once you put those in, you're going to get the outputs and you will get 5 points. We usually like to have 2 negatives if they're allowed to do the graph. And then you're going to connect and extend. So it might be a line, it might be a U, it might be a V, and we put our arrows on the end again if it's the right thing to do for the application. If it's a word problem, we put those arrows on to show it can go on forever. So welcome, guys. This is just the very beginning of doing some pretty cool graphs. I hope you all have a great day.